Hello and welcome to homework for part 3. In part 3 of this homework, we are asked to perform a von Neumann stability analysis to prove that the value of R that we use to calculate and plot the temperature profile for the bar in part 2, that we truly do have a boundary on that R value, more specifically an upper bound boundary of 0.5 for R dt. So what I have here is the equation that we used to solve and plot the temperature profile, which again is dependent on time. Again, we know that this R, we're just using as a parameter, and that R is delta T times the heat diffusion alpha and the thermal diffusivity alpha and delta X squared here on the bottom. And what I've written out here is the heat diffusion equation here. And what we found is that a solution to the heat diffusion equation is T is equal to E to the I K X multiplied by E to the negative alpha K squared T. And what we're going to do is we're going to transform this solution and put it in terms of the temperatures that we have expressed in our equation above here. So if we want to express this in Tj at the first time step here, n, we notice that what we will have to change here is this x as well as this t. So we'll have e to the I k, and x is just how far we are or where we are positioned on that bar. So that'll be j times delta x, and then we'll have e to the negative alpha k squared, and we know that t is equal to n times delta t. So n delta t. So now, if you notice, what we also will need to get is, let's say, t at j plus 1, so 1 to the right. And if we do that, all we simply have to do is change j here. So e to the I k j plus 1 delta x, e to the negative alpha k squared, and then n delta t. And if we want to go further, we see that these two are like terms here, so that this would also equal e. Distributing, we would have I k delta x, because we have j plus 1, and then distributing, these two are the same terms, so it's just tj comma n. So what we're going to do is we're going to go ahead and plug these terms in that we have now expressed in the temperatures in this equation. We're going to plug this in and see where that gets us. Okay, so what I'm going to do now is plug in the expression that we have found for temperatures. So bringing down Tj at n plus 1. Make it a little bit smaller. So n plus 1. So what I'm going to do is factor out Tj at n from all of these terms. So Tj at n. And for our first time, we'll be left with r, and that'll be multiplied by e to the negative I k delta x. We will add 1 minus 2r. And we will also add, our last term here is j minus 1, so we are shifting 1 to the left. So we will have re to the negative I k delta x. Now what we are going to use now is what is known as Euler's formula. So we have that e to the ix is equal to cosine of x plus sine of x, or excuse me, that's I sine of x. And this is utilizing Euler's formula here. So we have also that e to the negative ix is equal to cosine of x minus I sine x. Odd here, so negative. Okay, so now what we can do is we can go ahead and plug this in. So we have t j at n plus 1 is equal to, well, if we add both of these together, we will have two cosines. So we will have 2 cosine of k delta x, and then adding plus 1 minus 2r. Okay? Alright, so I think I forgot to write down our tj comma n term, but I've erased all of this and given us some more room. And what we're going to do here is look at this term right here. And what we notice is that if this term is greater than 1, we have the potential to drive our temperatures up to infinity. And obviously, that would be an issue. So what we want to do here is we want to take the absolute value of this term here and set it less than 1. So if we do that, I'm first going to combine some terms here. So we have 1 plus 2r. And this will be multiplied by cosine of k delta x, and then we'll be subtracting 1. So what we want to say is that if we have this term in the origin of, let's say, a plot here, we want the absolute value of it to be, we can do less than or equal to 1, and on the other side we will have a negative 1. So taking absolute value rules into effect. So what we want to do here is we want to see what our bounds are for our R. And remember, when we plotted our temperature profile, we obviously saw that we had a bound, in this case an upper bound for R, before our plot went a little crazy. So what we want to do here is essentially solve for R. So what I'm going to do first is subtract a 1 from each side. So I have negative 2 less than equal to 2R cosine k delta x minus 1. On this side we will have less than 0. And what we can see here is, so we have the left side of our inequality and the right side of our inequality. And what we can see is that the right side of our inequality is always true. This term here, if you look at it and look at cosine, for whatever values we have here, it is always less than 0. So we're simply just going to not negate this, but stop taking a look at the right side and just focus on the left side of our inequality. So if we simplify this down, what I'm going to do is divide over, and I'm also going to take out the negative sign, so we have to switch the inequality sign here. So what we'll be left with is 1 over 1 minus cosine k delta x and this, again, we had to flip the inequality sign solving for R here. So what we want to do here, again, is we want to see where our bound for R is. And we want to set that at the lowest possible value here. So what we can do here is we can say the lowest possible value that we have for cosine k delta x is negative 1. And if we substitute that in, what we get is that we'll get 1 over 1 minus negative 1, or 1/2. So R must be less than or equal to 1/2. And this makes sense because when we actually did this just by trial and error in part 2, if you remember, I showed if we go just above 0.5 in our time steps, or really our R is what we're looking at. If we go above that 0.5, that's when our graph gets real wacky and we go up to weird temperatures, and we can obviously see that something is not right. So this is again known as the von Neumann stability analysis, and we see that we do have an upper bound for our R value. Now what we're going to do in part 4 is basically allow ourselves to have no limitations on the bounds that we set in the parameter, or the parameters that we set in this problem when solving for the temperature profile. So we're going to discuss that more in part 4, but that will do it for part 3. Thank you for watching.